Okay. We are going to start with chapter 3. Okay. I hope everyone has done your tutorial 2. I have assigned all of you to submit your tutorial 2 so that I'm a bit confident that you yourself have been, doing some activities on the answering the tutorial questions. Okay. But for the discussion of the tutorial question will be done after I glance through all your answer given in your tutorial too that I asked you to submit in the Google Classroom. So somewhere next week, I think I'll just do that on the discussion on the tutorial too. Okay. So for this chapter, okay, so this is a continuation of your what we call engineering statistics. If we reflect back what you have done in chapter 1, we are dealing with data, okay, how we can use our engineering statistics knowledge on how to collect data, how to organize data, how to summarize data, and how to present your data using graphical and numerical representation. And finally, you can make some what we call interpretation from your analysis of your data. And in chapter 2, what we deal with will be on how we can understand whatever random variable that we are dealing with is actually related to certain probability distribution. Okay, and we know that what we have covered in chapter 2, there will be two types of probability distribution. The first one is discrete and the second one is continuous. And under discrete probability distribution, we have seen how an experiment is called as binomial experiment and how an experiment can be called as by Poisson probability distribution. And the last but not least will be the continuous probability distribution on specifically what we call as the normal probability distribution. And we know since normal probability distribution will involve variety of means, okay, since we are using the mean as the center value, and that center value reflect the probability distribution of our symmetric distribution. So we were going to have a different table of normal to be referred to whenever we want to find the probability. So what happens is that uh, to in order to just use one specific table to help us out with the normal probability distribution, we standardize them into what we call standard normal probability distribution. Okay, so in chapter 2, basically we look through the probability distribution of each of our random variable. Now, what happens if we have something that we need to do in extra? Okay, for example, what you do in chapter 1 or what you do with your data is using the graphical or numerical is no longer useful to you. You have to do more than using the graphical and numerical. So this is what you can have as an option to do that. Okay. So chapter 3 is about the statistical inference. Okay. Before I go through what are the things that we define as statistical inference, if you can see from your first chapter of chapter 3, okay, you can see there is a chapter outline. Okay, so what you can study or what you can understand from the chapter outline will be the things that we wish students to understand. Okay, if you look through, you will have 3.1 the introduction, 3.2 the sampling distribution, and 3.3 the inference for single population, followed by inference for two population, and finally we have non-parametric statistics. So if you go back to what we call as statistical inference, okay, we are referring to our population. Okay, let's say this is your population, and we know that in order to study our population, it will be hard for us to do that because it will require more time, more workers, more manpower, more money. Okay, so what we do, we focus on subset of our population. That is what we call as our sample. Now, using graphical and numerical is insufficient in our case. We need to do more. We need to dig more. We need to investigate more. So what happens is that we are going to use our data that we measure from our sample, and then we are going to use that to make our generalization for our population. So this is what we call as statistical inference. So from this, what we call simple annotation, I think you can imagine it will be far more what we call complicated compared to what we call statistical using graphical and numerical data representation. So whereby there will be a lot more involved when we do statistical inference. So when we do statistical inference, we will cater what if we have only one population. For example, this one. Okay, we have only one population. And sometimes it could be involving more population, whereby we can have population 1, okay, and we may have the second population, okay. And how are we going to tackle this kind of what we call statistical inference? What if we have one population, or what if we have two populations to deal with? Okay, and of course, if you can see, for single population, there will be specifically on the mean and the proportion, and for the two population, also mean and proportion. So now we know we only deals with population mean, okay, and population proportion. The same goes to two populations. So we are going to look at the mean of our first population and the mean of our second population. And the same goes to the proportion of our first population and the proportion of our second population. Okay, so this is what we are going to do in chapter 3. And we know that from our chapter 2, the last part is what we call normal probability distribution. The two that we are talking about here, okay, these two is dealing with a random variable that follow normal. Okay, means that our x random variable that we are studying is following what we call normal distribution. And as we know that not all cases in our world will be following this what we call normal. So what happens is that we are going to see the option if we have x random variable that is not following normal, so not normal data. What if we have not normal? So what option we can use to make a statistical inference for our x that is not following a normal probability distribution, and that will be captured by the last part that is on the non-parametric statistic. So when you see the word non-parametrics, means that it refers to data that is not following normal distribution. Okay, when we say not normal distribution, the distribution can be skewed to the right, can be skewed to the left, can be uniform, and whatsoever. You can have many more types of what we call non-normal or non-symmetric distribution. So that would be some of the introduction on the statistical inference. And of course, when you see at the bottom of your first page of chapter 3, you can see the learning objective of chapter 3. Okay, so please, class, please take attention on the things that we wish everyone to understand. That will be the things that we want students to what we call grab the knowledge and know how to implement or how to use all the things under chapter 3 will help you out when you need to do the statistical inference. Okay, so I want you to read it on your own. What will be the learning objective? But what I can simply say, the learning objective will again reflect the whole thing that what we need, that what I have just mentioned just now. Okay. Now, some simple introduction on what is statistical inference. Okay, we know that we are dealing with population. Okay, we know that we are dealing with population because by using the data from our population, our modeling, our analysis, our investigation will be what we call better if rather compared to using some part of our population. But knowing that it incur a lot of money, a lot of time, okay, more manpower needed, so there will be no option to use the sample from our population. So taking subset of your population, okay, and this subset of your population is what we call sample. Okay, so when we know that we need to do some investigation, and we choose our sample. How we choose? We choose the best is by using the random method. Okay, we select them randomly, and this will to make sure that our sample is representation of our population. Representation of our population. Okay, so that's why we need to make sure that the way we choose our sample is following a random procedure. Okay. Now, once you have collected your sample, what we do, we are going to measure the things that we wish to investigate. For example, if you wish to study on the weight, then you are going to measure the weight of your sample. If you are talking about the height of your subject, then you are going to measure the height of all your subjects selected in your sample. And from your what we call data, once you measure, you are going to have your data. Okay, and this data is called your X, and there will be some measurement. Okay, if you are talking about, let's say, is the height, then you are talking about the height of all your subject in your sample. For example, the height will be 157, 163, 155, 180, blah 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 blah. Okay, so this data, okay, will be measured, and this is what we call statistic. Last time we talked about this statistic, right? Any measures taken from our sample is what we call sample statistic. Any measures from our population is what we call parameter. For example, if you are talking about the mean, okay, if you are talking about the mean of your population, then we are talking about mu. And if you are talking about the mean of sample, we are talking about x bar. Okay, we are talking about proportion of our population. The proportion of our sample will be p hat. Okay, the variance of our population is sigma. The variance of our sample is s squared. Okay, and the standard deviation is sigma, and the standard deviation of sample is s. Okay, so by now I hope everyone is clear. When we talk about these parameters, okay, such as mean, proportion, variance, okay, or the sample statistic, let's say we have x bar, p hat, s squared, so you know what we are talking about. Which one is referring to sample, which one is referring to population. Okay, so far okay class? Class, so far okay? Is it okay?
Okay, madam.
Okay, thank you. Now, if I can summarize what we are going to do or what we are going to learn on the statistical inference, these are all the things that you are going to cover, okay, in your chapter. So we have statistical inference, we have parameter estimation, and we also have hypothesis testing. Compared between parameter estimation and hypothesis testing, I think this one would be a bit challenging. Okay, challenging. Okay, this one is kind of easy. Okay, because it is straightforward, but require your meticulous touch whenever you do the solution for this particular parameter estimation. Because when we are dealing with hypothesis testing, you are going to have your statement of hypothesis. You will have to decide your decision. Then you have to remember what will be the decision. The decision refers to and everything. Okay, compared to parameter estimation, it is kind of straightforward. So under parameter estimation, we will have two types of estimation. That will be point estimation and interval estimation. And for interval estimation, we are going to look at the mean and the proportion of our population. And for hypothesis testing also, we are going to look at the mean and the proportion. And of course, when I said this just now, remember, we don't have the population data. We only collect the sample. We measure the things that we need to investigate. We have all the measurement. What happened? We are using the sample statistic to make decision for the parameter of your population. Now, these are the things that we study, but in the end, we are going to make conclusion about our parameter. So this is what happened in statistical inference. Okay, we are using the sample statistic to make conclusion of our parameter of our population. So when I say this, we are going to make conclusion about mu. We are going to make conclusion about proportion by using what? By using the X bar, by using the proportion of our sample. The same goes here. Okay, so this is for one population. Later on, we will see how to deal with two populations. Now, if you look at your textbook, can everyone please turn to your textbook on page 75. Okay, page 75, there is a subtopic what we call sampling distribution. Now, this sampling distribution is actually, if you are studying a statistic, sampling distribution is a big topic that needs to be covered. But because this sampling distribution is the basic knowledge of statistical inference. Okay, but since you are not measuring in statistics, we feel that you need to understand what do we mean by sampling distribution and how what does it has to do with the statistical inference. Okay, now imagine this way. So if you look at your textbook, the last paragraph, okay, for example, suppose I'm not going to go through all the terms that is highlighted in turquoise color. So I wish everyone can read on your own because I need to be very quick for tonight's lesson because I'm going to cover until proportion for one population. Okay, so if you look at the bottom of the page 75, for example, suppose a sample of 35 students drawn from population of all Unimed students and the mean sample of CGPA is recorded. Okay, if you repeatedly collect 100 samples randomly of each sample size 35, the sample mean is based on the distribution of all sample mean CGPA of 100 sample means. What does it mean? Okay, class, imagine this way. In statistics, there is an understanding of what we call population. When I say POPN, is population. Population and sample. Okay, we believe that if we have some measure for our population, for example, if we say, let's say the weight, the weight of a student, okay, uh, let's say 75 kg, okay, we believe that the sample also may have what we call weight of 75, or could be lesser, or could be greater. The same goes to, if we are talking about sample, the same goes to what happened to the population. So we believe that if we sample out different sample, for example, imagine I have a population this big, this what we call the one that I uh, what we call draw now is my population. If let's say we are referring to all UNIMAP students, okay, and we are talking about the CGPA, okay. Now we want to find the average CGPA or the mean CGPA for our student. So we believe, okay, what we believe is that if we sample out, for example, my population, okay, and let's say just put it 7,000 students, okay, UNIMAP students 7,000. So what happened if we need to find all the CGPA of our 7,000 students? It will be a bit time consuming. So what happened? We just sample out. So we sample out few samples. So in this case, let's say we sample from first sample, second sample, and 100 sample. So means that from our 7,000 population, I sample out the first sample where the sample size is 35. Then I sample out another sample, second sample, the same sample size, 35. I get my mean CGPA for second sample. Then from my first sample, I can get my mean CGPA for first sample. And if I repeat this until my 100 sample, the same sample size, 35, I will get my mean of CGPA for my 100 sample. So what happens is that I will have this CGPA mean, second CGPA mean, third CGPA mean, fourth CGPA mean, until the 100 CGPA mean. Okay? And if we total up the mean of our CGPA, we can get our what we call estimation of our population mean. Population mean of what? Population mean of CGPA. So we believe in statistic it works this way. Okay, so that's why the sampling distribution tells you or prove in some way if you only sample once. So in reality, we are going to use to do this once only. You only do once only. We are not going to repeat again and again because we know that the nature of our investigation, if we sample out 100, it will almost give almost the same estimation of our mean or our proportion. So if I were to what we call present that in terms of our distribution of our sample 1, sample 2, sample 3 until my 100 sample, you can imagine this way. Okay, imagine the big distribution here is for your population. It's your mean CGPA of your 7,000 students of UNIMAP. So what happens is that what we can see is that if we are referring to our first sample, sample 1, so we will have our mean of our CGPA from our sample 1. The same goes to second sample. Let's say this is our second sample. So we may have second CGPA, mean CGPA. The same goes to the third one, the fourth one until our X n sample, x 100 sample. Okay, and what can you observe from this particular what we call distribution class? Can someone please tell me what can you observe from here before I give my what we call conclusion for this particular sampling distribution? What can you observe from here? We have the population distribution, we have the mean of our sample distribution. Class? Class, anyone? Anyone want to try? What can you observe from this particular diagram? Anyone? Anyone? No one bother? Class? Hello? What can you observe, class? From here? Class? I need to hear someone. What was that? What was that?
The graph is not same.
The graph is not the same. Any other comment? Any other comment? Any other comment? So sometimes this is what depresses me if I have online class, because it will be click, click, click. No one is talking. Okay. Anyhow, thank you for those who for the one that responded just now. Okay, what can you observe is that all the distribution of our sample is inside the population. All of our sample means how many? We have 100 sample means, right? All of our sample means are inside the population mean. Right. So this has been proved by the statisticians. So whenever if you repeat it again, this is what happened. So you can see that particular what we call a conclusion on page 76. Okay, sampling distribution of sample mean and sample proportion and the relationship between population distribution and sampling distribution on page 76. This is what has been explained. Okay, page 76. Okay, explain this actually. Okay, so I want you to read on your own. Okay, what are the conclusion when we do the sampling distribution, and if we what we call can estimate from these particular different samples, this is what we have. Okay, we can say that the estimation of our population mean. Okay, the estimation of our population mean, okay, can be obtained by our sample mean. Or if I were to be specific, can be estimated. Okay, in this case we are talking about point. Okay, can be estimated by our sample mean. So how does our population or sampling distribution represented? So this is how the sampling distribution of our mean. X bar is normally distributed with mean X bar and sigma squared X bar is given by sigma squared over N. Okay, so that would be the sampling distribution of our mean. Now, is there any question before I proceed? Okay, I hope the gist of our discussion here is that the sampling distribution is the backbone of our statistical inference. But due to some limitation, what we do, we are going to sample once only, and from our sample that we collected, we believe to be representative of our population. We collect our sample, and what we find at the end of the day can be representative of our population. Okay, so that is the gist of this particular discussion. Now, let us move to the 3.3 that will be on page 77. Okay, it's inference for single population. Now we are talking about a population, okay, one population, and what if we want to what we call estimate on the sample population of our mean and of our proportion. Now, before we begin with the interval estimation, let us look at the point estimation. What is point estimation? Okay, a point estimate is a single value estimate of an unknown population parameter. If let's say you are talking about weight, then the unknown of our population weight. Okay, what about the interval estimate? An interval estimate is a range of values around a point estimate used to estimate of an unknown population parameter. For example, if you are talking about point, exactly we are talking about one single value. Okay, that is what we call as point estimation. Okay, now if due to this particular what we call situation, okay, there will be a case whereby point estimation will not be helpful for you. Okay, knowing that our sample will be varied. Our first sample, second sample, third sample, until our end sample, there will be different values given based on our different samples selected. Now, knowing that this is what happened in real, okay, therefore, there will be a need for interval estimation. Okay, so we may have point estimation, or we may also have what we call interval estimation. Okay, so if you can see for the interval estimation, the point estimation is also used in your interval estimation. So this is the point of our X bar. Okay, now let's move to the I'm 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 a bit jumping here and there because I need to give you the whole or the clear picture. How does chapter 3 works for your understanding? Okay, so those subchapter or those paragraph that I did not touch specifically, so I want you to read on your own and try to relate to my what we call explanation to that. Okay, so if you look at your page 77, okay, on point 3.3 on inference for single population, okay, we begin with the some understanding of what we call uh, point estimate is 77. Sorry, so you can look at the page 78. Okay, we are talking about page 78. Now, for point estimation, you just measure. Okay, for example, if you are talking about weight, what you do, you measure your sample, then you calculate. So if you are talking about mean weight, okay, you add all the weight, okay, you add all the weight, for example, 100, not 100, okay, you add all the weight, add on sample weight and divide by n. So you can get your X bar. That is point estimate. Okay. What if, knowing that my point estimate may not be what we call precise. Okay. So when we know that using a point, single point, may not give our answer for our population mean, or for example for population proportion. What option do we have is to come up with the interval. So how are we going to do it to deal with interval? Okay, so this is what is elaborated in page 78. Okay, this is what we call as confidence interval estimate for population mean. Let's say we begin with the population mean first. Okay, when we talk about confidence interval, okay, confidence interval, or afterward I'm using CI. So CI stands for confidence interval. Okay, so when we do or when we search for confidence interval, so there will be some confidence level involved in our calculation. So the most common calculation of confidence level will be 90%, 95%, 99%. So this is the most common. Okay, is it okay if we find confidence interval for 98%? Can. Can we find confidence interval for 92%? Can. Okay, but most of the time, researcher will use these three, what we call confidence level. Okay, so what about this confidence level that make or that create your confidence interval? Now, when we say confidence level, so there will be some level of error. Okay, your alpha. For example, if you are talking about 90%, okay, so if you relate to your probability under the shaded area of your normal probability distribution, so this is what we call 0.90, the probability value. This one is 0.95. This one is 0.99. Okay. Now, where is the what about the rest of our what we call probability? So if this is the case, if we have 90%, then our alpha is 10%. So in this case, alpha is equal to 0.10. Since we are dealing with interval, so there will be left and right interval. Okay, so that's why our alpha will be divided by 2. Okay, and this becomes 0.05. Okay, when you have 0.05, so please look at your second table, upper tier probability distribution. Look for alpha 0.05. I'm sorry, a bit small. Okay, for alpha 0.0500, so you will have your Z alpha, or what we call as critical value. Okay, Z alpha, or you can write as Z 0.05 is equal to 1.6449. Where is 1.6449 is along your x-axis, somewhere here. Okay, and this is your alpha 0.05. I think we'll just use another color. Okay, to differentiate. Okay, so this is your alpha over 2, that is 0.05, and this is your second alpha over 2, that is 0.05. And if you calculate, you get complete 100%, okay, the total probability. That if you are talking about the confidence level of 90%. Okay, for 95%, so we have another 5%, so alpha is equal to 0.05, right? Okay, 5%. So divide by 2. Divide by 2. So you will get 0.025. That's right. Okay, 0.025. So how do I know? I know that this is my 0.025. So this is my alpha over 2, 0.025. This is my alpha over 2, or my critical value. alpha over 2, that is 0.025. And what is my critical value here? So the critical value for 0.05, sorry, 0.025 would be 1.96. 1.96. Okay, so that's how we use our upper tail table to find our critical value. The same goes to 99. So for 99%, so there will be alpha equal to 0.01 divided by 2 divided by 2. So you will have 0.005. So 0.005 is 2.4, 2.5758. Okay, so that will be your critical value. So you know that your critical value is along at the x-axis. X-axis, huh? Okay, now what is this for? So we are going to use this alpha level, confidence level, critical value to find our interval estimate. Okay, interval estimate of what? Interval estimate of mean and interval estimate of proportion. Okay, any question so far, class? Any question?
No, ma'am.
Okay, thank you. Now we proceed with the some concept of the confidence interval. Okay, now before I proceed now, can someone comment on the what we call on the confidence level and the what we call the interval in terms of the interval? Or I will just summarize for you lah. Okay, if you can see from here class, from this red diagram, okay, I'm using my, let's say I'm using my blue pen. Okay, for 90%, this is the your interval will be between these two values only. If you are talking about your mu, so your mu will be between this value. Okay, what value? Not this value. This value is your critical value. Okay, if you are referring to x, the mean, so there will be the mean will be ranging from this interval to this interval. If you are talking about 95% confidence level, okay, so the interval will be a bit bigger from your 90%. If you have a 99% confidence level, so your interval will be even bigger, right? So you can see the larger the alpha, the smaller the interval range. The smaller the alpha, okay, the larger the interval range. Am I saying the same thing just now? I repeat again. The larger the alpha, for example, this one is the larger alpha, 0.10. 0.10, it will give you smaller interval. I'm sorry. Okay. Larger alpha, smaller interval. Smaller alpha, larger interval. Okay. I made it. I think it will be better for me to write. Larger alpha, smaller interval. Okay. Smaller alpha, larger interval. Am I right? See? Smaller alpha, larger interval. Larger alpha, smaller interval. Okay? So because this understanding sometimes will be asked, okay? Especially when we are talking about what we call online, okay? And you have the online assessment. So if we have more calculation, it will be not good for you to score for your assessment. So we are going to balance the theoretical questions and the calculation questions so that we can assess you how far you can understand the whole things covered in the chapter. Okay. Now let us look at the what are the things that you need to know when we are talking about the confidence interval. Other than confidence level, alpha, critical value, okay, there will be one more thing that you need to know: margin of error. Okay, so the margin of error, okay, for example, if I'm talking about the x bar is equal to, let's say, 75, okay, And we know that the interval is between what am I going? Okay, let's say 60 and 80. Sorry, 90. 90 lah. So 90. So what happened is that, okay, if I have x bar plus minus, let's say I'm using one of my calculation of CI, confidence interval. I have z alpha over 2 sigma over square root of n. Okay. Now, this particular from the point estimate to the what we call lower confidence limit is what we call the margin of error. Okay, margin of error. The same goes to the point estimate to the upper confidence limit. So this is the range here is what we call margin of error. Okay, so if you have margin of error 5 here, there will also be 5 here. Okay, there will be symmetric margin of error. Okay, so where does this margin of error came from? It came from this one. Okay, contributed by the plus minus here. Z alpha, the critical value. This is the critical value and the standard error. Okay, so that is given for the margin of error. Okay, so that will be among other things that you need to aware of the confidence interval, because margin of error mostly will be used in a question regarding finding the sample number of samples involved in your investigation. Now, let us go through to the first example of how we can find the confidence interval if you are talking about the mean of our population. Okay, so look at the topic class. Confidence interval estimate for population mean. We are trying to do the estimation for population mean. Bear in mind, we don't have the data for our population. Now, this is based on samples only. Sample collected. Okay, and our aim will be at the end of the day, by having the x bar, we are going to estimate about the population B. Now, there will be few what we call conditions that you need to know on how to find the confidence interval for the proportion B. So there will be three conditions. Okay, the first one is if you know what is your population variance. So this is sigma. Sigma refers to population variance. Sorry, population standard deviation. STDEV, standard deviation. So this is sigma. Now, whenever you have equation, okay, in your equation, identify, is your sigma given or known, or is your sigma unknown? If your sigma is known, means that your calculation of your confidence interval will be based on sigma. If you are not given what is your sigma from your equations, so there will be two conditions that you need to look into. The first condition, if the n is greater than 30. And the other one, if your n is less than 30. Why there are such cases when you have n greater than 30 or less than 30? Now, class, remember. For example, if you're talking about experiment, okay, and that particular experiment involves very expensive materials, okay, and the procedure would be very fragile, okay. So what happens is that there will be time where you need to be based on very small sample. For example, n may be only 50. Okay, so this particular option will give you on how you can find the confidence interval for your experiment. So please look at the condition of your sigma, whether your sigma is known or unknown. And if your sigma is unknown, look for the n is your n greater than 30 or less than 30. And if it is greater than 30, so your sigma is estimated using sample standard deviation. So sigma is estimated using sample standard deviation. Okay, sample standard deviation. What if my n less than 30? Now remember class, you have, if you look at your standard normal distribution, before your standard normal distribution, you can see t statistic. Okay, so this is what we call t statistic, student t statistic. Now this is kind of a sister of normal distribution. Okay, a sister. They are, this distribution is still normal, but it has different, what we call different from the normal distribution. Okay, so this is what happened if your n less than 20. Now for t, the critical value will involve alpha over 2, and the second parameter is your v. And this v is obtained by n equal to, your v is equal to n minus 1. Okay, v is equal to n minus 1. The sample size deduct by 1. Okay, so this particular term is what we call standard error of the sample mean. Okay, so this one is the critical value. This one is the critical value. Okay, this one is the standard error for the sample, for the sample mean. Okay, and this is your sample mean. We are dealing with sample mean. Okay, for the estimation as inference of your population mean. Now, if I summarize on how to find the confidence interval for the population mean using the sample mean, so this is how all the formula of the calculation. Okay, if sigma is known, x bar is plus minus z alpha over 2 multiplied with the standard error. If sigma is unknown, n greater than 30, so you will have, this is your margin of error or the interval for the lower confidence limit, and this is for the upper confidence limit. Okay. Now let us look at the example. Okay. Example 3.1, that will be on page 80. Okay, page 80. How are we going to start answering these particular questions? Okay, now a random sample of size n 20 students is drawn from population of interest with known standard deviation. Based on sample data, okay, based on sample data, it is found that the mean student weight, okay, mean student weight, okay, x bar equal to 64.3 kg. Construct 95% confidence interval for the population mean if sigma. See, this is what we call a hint for you. Whether your sigma is known or unknown, then this is the hint. Okay, construct and interpret 95% confidence interval for the population mu if sigma. Then this is what we call known sigma. Okay, sigma is 15. Now, okay, what is your mu? Mu in our case is the population mean weight of all students, because we are talking about population, right, of all students. So this all students shows the population. Okay, so that's why we define that way. So we know that we need to find x bar plus minus z alpha over 2 sigma known. It will be based on sigma over square root of n. Okay, so let us find the alpha first. Okay, so your alpha here is 5%, so it will be 0.05, and you need to divide by 2 because 2 tail, so you will have 0.025. So your z alpha over 2 is equal to, if you look at your table, so you will get 1.96. Okay, 0.025. Okay, 1.96. Okay, now let's begin answering. Okay, so you know that your x bar is 64.3 plus minus 1.96. Okay, multiply by sigma is 15 over square root of n. Your n is 20. Now, class, why am I using uh this one? Whereas I know my n is 20. Class, can anyone comment? Class, anyone wants to comment? Once you know that your sigma is known, you will have to use this formula, regardless of what your n value, your sample size is. Okay, but if your sigma is unknown, then you have to watch out which condition refers to your problem. So in this case, that's why we're still using this particular what we call formula. So in this case, so you will have 64.3 plus minus, if you calculate, your margin of error would be 6.57. Okay, so you will get following your answer, it will be 57.73, and the maximum value, the upper confidence limit is 70.87. Okay, so or you can write as your mu is greater than or less than 57.73 or less than 70.87. Okay, so you know that if you draw, okay, if you draw and you know that you are talking about the estimation is 64.3, and let's say here is 57.73, here is, let's say, 70.87. So this is what we call 95%. Okay, so this is how your interval looks like. Okay, so that will be example 3.1. What about example 3.2? A researcher conducts a survey to determine mean waiting time for a treatment at emergency room or from several government hospitals. So you are talking about mean waiting time in emergency room for different government hospitals. So let's say the how many government hospital, for from a random sample of 30 emergency room, it is found that the sample mean waiting time, okay, so the sample mean waiting time is 174.3 minutes. With the standard deviation, now this is your hint. With the standard deviation, what does that mean? This standard deviation is calculated from your sample. So your S is 40.3. It's not your sigma. So in this case, sigma unknown. Okay, and you are talking about 99% CI. So let's say we look for CI first. Alpha equal to 0.01 divided by 2. So you will have 0.005. 0.005. So you will get Z 0.005 is equal to 2.5758. So the interval would be, so this would be 174.3 plus minus 2.5758. Okay, multiply with unknown sigma. So your n is 30. So you are fulfilling the condition for this particular case. Okay, so you will have 40.3 divided by square root 30. So you will get 174.3 plus minus your margin of error is 18.95. So if you calculate your interval, okay, it will be from 155.35 until 193.25. Okay, so you can also write as 155.35, 193.25. So now, how do we conclude? How do we conclude? So we conclude that we are 95% confident that the mean, what was this? That the mean weight of all students, okay, of all students is between 57.73 and 70.87 kg. Please put the unit. Okay, so here we are 99% confidence that the mean waiting time for a treatment, okay, for a treatment at emergency room is between 155.35 and 193.25 minutes. Okay, so that's how we deal with the interval. Now, let's look at the exercise. Okay, why don't we try exercise number 2? Because the exercise is a bit longer, so I want you to try exercise 8. Right, yeah? So let's look at the second question. Score in EQT 203 subject for a random sample of 8 students in a class of 150 students are given by this one. Now, if you read it carefully, some of you might be confused. What does 150 students mean? Class? Okay. A score in EQT 203 subject for a random sample of, so we know that this is our aim. In a class of 150 are given by. So I guess this is your population. Okay. So since we are not going to look at after 150 students score, we look only for 8 samples, 8 students for our sample. Calculate the mean, score, and the standard deviation. Do you still remember how to calculate the mean and standard deviation, class? Plus, so if you are looking for the mean, x bar would be 70 plus 72 plus 65 plus until plus 78. Divide by how many? 8. So you will get your x bar equal to 73. Okay. What about standard deviation? Okay, standard deviation, let's say we begin with S squared variance. So it will be the deduction of each score with the mean. So you will have 70 minus 73 squared plus 72 minus 73 squared plus until the last value is 78 minus 73 squared. The whole thing divided by n minus 1 because we are calculating the sample standard deviation. So S would be square root of, so S if you calculate on your own, okay, S will be given by 5.15. Okay, so that would be a question number 1. Construct a 90% confidence interval estimate for the mean score for all students in the class. Okay, now based on this, what we call 8 scores, we want to infer or make inference for all 150 students. Okay, see what happened. So for second question, let's say I do it here. Our alpha is 0.10. Alpha divided by 2, you will get 0.05. So Z 0.05 is given by 0.05, 1.6449. So X bar plus minus 1.6449 multiply with standard deviation is 5.15 divided by sample size. So our sample size is 8. Oh, sorry. What did I do wrong here, class? Class, what did I do wrong here? Class, can someone trigger what the mistake that I made here? Anyone? What mistake I did here? Class, is this correct? Class, is this correct? Can someone reply? Is this correct? Am I alone here? Maybe I stop for a while. See how many of you are inside. Now, class, what did I do wrong? Class, this is right. Why? Because our n is 8. Okay, our n is 8 less than 30. If less than 30, it should be x bar plus minus t alpha over 2 v multiply with s over square root of n. Right? Okay, so if I'm not aware with the condition that I need to fulfill, then I make wrong. I make mistake. Okay, so knowing that this following table of what we call so this one is no longer applicable. So x bar is 73 plus minus. If you look at your T alpha over 2V, let's see, I open my okay. Let's look at our T distribution. Can you see my slide here, class? Class?
Yes, sir.
Okay.
Yes,
Our,
sir.
okay, thank you. Just now we say our T, okay, T is alpha over 2 V. And we know that our alpha is, what is our alpha just now? 0.10, right? 0.10. So alpha over 2 will be 0.05. Right. So 0.05. So P alpha over 2. Okay. So 0.05 and V is defined as n minus 1. So 8 minus 1 will be 7. So this is how we see our table. So look for V7 and for our alpha 0.05. Okay. So this is our critical value. So this one is given by 1.8946. 1.8946. So here we know that our critical value is 1.8946. Multiply with standard deviation is 5.15 divided by square root of 8. So you will get 73 plus minus. The margin of error is 3.45. Okay, and if you calculate, okay, you will get your answer would be between 69.55 until 76.45. Okay, so we know that we can conclude that we are what 90% confident that the mean the mean score of EQT 203 of all 150 students is between 69.55 and 76.45 no unit. Okay, because it's 15 to score. Okay, class, clear? Okay, which formula suitable for this problem? This formula. Why? Because n less than 30. Okay. Construct a 95% confident interval for the mean score of all students in the class. So number 3. So for 0. So alpha divided by 2, 0.05 divided by 2, you get 0.0. 0.025. Yeah? So if you look for P 0.025, 7, what is the value? 0.025. 0.025. 0.025. So you will have larger margin of error, 2.3646. 2.3646. 2.3646. So you will have 73 plus minus 2.3646 multiply with 5.15 divided by square root of 8. So you will get 73 plus minus 2.3646 multiply with 5.15 divided by square root of 8. So you will get margin of error even larger, 4.30, or estimate in approximation is 4.31. So your interval would be between 77. 73 minus 4.31, you will get 68, 68.69 until 77.31. Okay, so we are 95% confident that the interval, that the mean score of EQT 203 of all 150 students is between 68.69 until between and 77.31. Okay, so if you compare, okay, if I were to what we call draw, okay, if I were to draw, the mean is 73, okay, for 95%. So let's say we begin with 90%, okay. For 90%, so it will be 69.55 until 76.45. Okay, so that would be for 90%. For 95%, so you will have 60, let's say 68.69 until 68. You have 77.31. Am I correct? Okay, 68, 77. Yeah. 76, 77. 76, 77. Okay, yeah. 68. Sorry, 68 is not here. No wonder I felt something wrong with the now 68 would be somewhere here. 68.69 and you have 77.31. So this one is for 95%. So sometimes you will need to do your interpretation. So this kind of interpretation might be asked in your assessment. So you need to know how to interpret. So if you have what we call larger alpha, when you have larger alpha, means that your alpha is over here and over here. You have larger alpha, you have smaller interval. If you have smaller alpha, you have larger interval. So the one that I mentioned earlier. So you need to know how to justify or compare or what we call compare and contrast your answer you get. Okay. Any questions so far, class? Any questions so far?
No,
Okay. If no question, I need to drink some water because my voice kind of I lose my voice. I'm losing my voice for at the moment. I don't know how to pause. Okay. Now, I want you to write something in the chat room so that I can check whoever attend the class today. Okay, can you please start writing your name so that I know who are presenting, who are who are absent or who are not absent. Okay, please. Okay, thank you. Okay, I'll go back to my slide. My last part before we stop. Okay, now we finish with the single estimation for population mean. Okay, now what if we have proportion? Okay, and why do proportion is involved and it is meaningful in our interpretation? Okay, now let's look at the concept of confidence interval estimate for population proportion. And you can refer that on your textbook on page 82. Okay, now what is confidence interval estimate for population proportion compared to confidence interval estimate for population mean, which has few conditions? Proportion is kind of straightforward. Okay, because you will never deal with condition for a calculation, because we are referring to proportion, and usually the proportion will involve large sample size. Okay, so when you have large sample size, so most of the time the way we calculate, we will use proportion to represent our what we call our estimation, and that estimation, that is proportion, will be used to make inference for our population. Now, unlike mean, we have x bar plus minus z alpha over 2, and if sigma is known, then we have the standard error is sigma over square root of n. Or if your sigma is unknown and your n is greater than 30, so you are going to use your sample standard deviation. But if your sample standard deviation, if your sigma is unknown and your n is less than 30, so you will have to use plus minus t alpha over 2 d and s over square root of n. But for proportion, you will always be using p hat plus minus z alpha over 2 square root p hat 1 minus p hat divided by n. So in this case, we will always use critical value z alpha over 2 because large sample. Okay, because of we are dealing with large sample, most of the time we are going to use the critical value obtained by the standard normal. Okay, as this one. So, okay, how what are the things that you need to know? The most important thing is this one: how to calculate the proportion. Okay, the proportion will always be calculated based on the x. This x is the determining, the things that is determined or characteristic determined in your question. Okay, for example, it could be the number of unit with characteristic of interest in the sample. Okay, if you are talking about a computer chip, if you are talking about the defective, then X is the number of defective chips. If X is referring to non-defective chips, then you are referring to the number of non-defective chips. So look at the given X or the characteristic in your given questions, and you will divide by the number of samples. You will get the proportion of your sample. Okay. Now let us look at the first example. Okay, the first example on page 3.3 is on page 82. Okay. Now let P be the proportion of all students with limited amount of time for self-learning, and P hat the corresponding sample proportion. Sample of n 1,500 students are randomly selected, and it is found that 600 of students agreed that they have limited amount of time for self-learning. Construct and interpret 95% confidence interval for the proportion of all students who have limited amount of time for self-learning. So take out all the information given in your question. Okay, the first one is n 1500. Okay, the x is 600, referring to the if you are referring, the p will be referring to the proportion of all students with limited amount of time for self-learning. Okay, so then X is referring to this particular sample proportion of all of students who have limited amount of time for self-learning. So in this case, you can find your P hat, that will be 600 divided by 1500. Okay, so you will get 0.4. And you need to find for 95% CI. Okay, so 95% CI means that your alpha is equal to 0.05 divided by 2. You will get 0.025. Now class, it seems simple because I'm doing it for you and you have your book. Okay, but in the assessment, this is what usually students forget. They forgot to divide by 2. Okay, so when they forgot divide by 2, so they are going to refer to alpha is 0.05, which will give you different answer of your critical value, and definitely it will affect your final answer. So please be careful when you are calculating. So for Z alpha 0.025, we know that it will be 0.025. It is given by 0.025 is 1.6996. So write down everything in terms of the CI. So you have P hat equal to 0.4 plus minus Z alpha is 1.96 square root, okay, 0.4 multiplied with 0.6 divided by the number of n is 1500. Okay, so if you calculate, this would be 0.4 plus minus the margin of error. So I like to use the calculation of the margin of error instead of using the textbook way. So square root 0.4 multiplied with 0.6 divide by 1500 multiply with 1.96. So you will get 0.0. Let's say I take two decimal point, 0.02. Okay, so if you deduct, you will get your interval would be from 0.38 until 0.42. Okay, so how do we what we call interpret? So we are 95% confident that the proportion of all students who have limited time for self-learning is between 0.38 or you can put it in percentage, 38% and 42%. Or you put it in terms of percentage, it will be 38% and 42%. Either one can. Okay. Any questions so far, class? Any question? Okay. If no questions, there is a question for exercise. Let's say I answer question 2. Okay. So please try this question. Okay. Now, question 2, Hassan and Nizamiani wedding ceremony will be held at KLCC Convention Center soon. A survey is carried out to estimate. Can someone tell me what is the time now? What is the time now, class?
10:34, madam.
10:34, so half an hour. Okay. Thank you. So, Based on a sample of 250 invitations, 180 returned the card and agreed to attend the ceremony. Construct a 90% confidence interval for the proportion of all invitations will be agreed to attend the ceremony. Interpret the interval. Now, take out all the information given to you. So, the first one is sample, n is equal to 250. Now, 180 return the card. Okay, so your x is 180. Okay, and your CI will be 90% CI. And your proportion here is defined as the population, the population or the population, the proportion of all, so you can see, of all invitation, the proportion of all invitation, the proportion of all invitation agreed to attend, agreed to attend the ceremony. Okay, to attend the ceremony. Okay, so begin with the proportion P hat. Did I put P hat just now? Okay. Remember class, notation is very important. Sometimes we may ask you, you may calculate it right, but the answer option will be P only. So please, if you are talking about proportion of your sample, P hat must be the correct notation. Okay, so please make sure. Statistic, when it comes to calculation or what we call assessment, it is easy for us to set equations, but give you wrong notation but correct answer. Wrong answer, correct notation. Or either one or both are correct, then that will be a correct answer lah. So please make sure and be more meticulous in terms of looking at the notation. Now, so your P hat in this case would be 180 divided by 250. So you will get 180 divided by 250. So you will get 0.72. Okay, so when you do your solution, put it in a nice way, because I'm using my limited area, so a bit chaotic. So alpha is 0.10 divided by 2, so you will get 0.05. So z 0.05 is equal to what? 0.05 is equal to 1.96. Okay, so P hat plus minus Z alpha over 2, or we just simply put accordingly. So you have 0.72 plus minus 1.96 multiply with 0.72, 0.28 divided by square root of 250. Square root or not square root? Not square root. Okay, so you will have 0.72 plus minus, so square root 0.72 multiply with 0.28 divided by 250, you get 0.028 multiplied by 1.96, so you will get 0.06. Okay, so if you calculate this, you will get 0.72 minus 0.06, you will get 0.66 until 0.78. Okay. Okay, so in your textbook, a bit more or less lah. So in your textbook, the answer is 0.67 until 0.77, more or less the same. Approximation. Okay, so now how do we interpret this? Then we can say we are 90% confident that uh, the proportion of all invitation, and maybe it's better for me to write it. We are 90% confident that the proportion of all invitation agreed to attend the ceremony is between 0.967 and 0.77. Okay, 67%, or you can say 67% until 77%. Or if you convert this into the number, so 67% would be 0.67 multiplied by 250. More or less 167. 168 people. Okay, so you can simply put that in. So for any question, class? Class? Are you all okay?
Madam.
No.
Okay. Do you want me to stop or do you want me to continue until what I have prepared?
This is
Stop,
enough.
madam.
This is enough.
You cannot go, because for your information, class, chapter 3, we need to complete within 3 weeks. Okay, I'm among the almost the same lah. The rest of the rest of the lecturer, some of them start uh, teaching the chapter 3 this week. So some of them start next week. So the course coordinator require us to finish teaching the chapter 3 within 3 weeks only. So imagine I have, and many of them they have only sync class that will be only 2 hours during the day, and the async class they assign the video. But for me, I'm not really keen of giving you a video, short video to certain topic, because I'm not feeling confident that many of you will review or view the materials and understand the concept. That's why I prefer to teach during the sync and async class, because I need to make sure that everyone can understand the things that need to be covered. Because the way I explain, even though not as good as good lecturer, but at least I give you some more insight when I myself explain to you the materials of the particular chapter that we discuss. Okay, so I hope because the number of viewers of the video are not really what we call many. So I would like to ask you, do you still need the recorded video or not? Because let me stop recording for you, okay? Because what, class?